All right, so now let's look at the various instabilities that were observed in this situation. So the first one is a longitudinal mode. So this is, in this case, it comes out because the frequency of this mode is very low, and so it falls in the range of receptivity of the flame. And all the microphones, how is it manifested? If you look at the microphones, which are located here, the 5 microphones, they're all in phase. Essentially, the signals on the microphones are nearly the same. They are in phase. And if you look at the power spectral density, it has a very strong peak at 252 hertz. There is also a harmonic, but much lower. But so this signal is very sinusoidal. And in terms of flame dynamics, one sees, so when red, it means very positive. When blue, it's very negative. Dark blue is very negative. So what one sees is that basically all the flames have positive heat release rate fluctuations. And then they become very negative right here, and this is in between. Not quite so. A few flames are not exactly synchronized with the others, but essentially most of the flames. So the whole thing is synchronized by this longitudinal mode, and at the value of pi over 2, of course, everything is neutral here. And here again, it's 3 pi over 2, it's neutral. So this is very positive, this is neutral, very negative, this is neutral. Let's now look at the modes that we have, these azimuthal modes. And if you have these 2 waves, it is very interesting to actually determine what we call a spin number. This concept was initially introduced by Stéphanie Évêque and Wolfgang Polifke. They were just wanting to characterize the amount of spinning in such a situation here. However, their definition is somewhat ambiguous. There is an ambiguity in using that definition. So this one is a better one, I think. So we have the amplitude A minus the amplitude B divided by the amplitude A plus B. So for example, if A is equal to, if you have A is equal to 1 and B is equal to 0, S will be 1, and the mode is rotating in the positive theta direction, that is in the counterclockwise direction. If A is equal to B, so in this case, S is equal to 0, and this is a standing mode. You get a cosine or a sine of theta minus omega t, so these are standing modes, and in fact, this is a standing mode. What you see here is you have a nodal line, this is negative, this is positive, and then you have the nodal line at another part of the cycle, this is positive, this is negative. This is a standing mode. However, a spinning mode is something like that. You have the nodal line, which is here, but at a later time, the nodal line is here, and this rotates. What is the speed of rotation of that? The speed of sound. So it rotates at very high speed. It's a spinning mode. And in between, well, it doesn't look quite like that. So in between, you have to put A and B, and you will see that there is it's a combination between something which is standing and something which is spinning. So it makes something unusual. And how is it manifested in terms of the microphones? When you have a standing mode and you look at the microphones, this is how they look like. So some microphones are like that, the others are on the other side. So when the pressure is positive here, it's negative there. When it's Negative here, it's positive there. You see, you have this sort of distribution for the microphones. If you have a spinning mode, this is how the microphones look like. It's a wave-like distribution of the pressure. And how does one characterize that? Well, using the spin number. Now, how does one get A and B? In fact, the problem is to get these two amplitudes. And once you get the two amplitudes, you can calculate the spin ratio. You have a signal on 5 microphones, but you have also only to get two quantities, A and B. And you know that the pressure P1 is equal to exponential I theta 1 times A times exponential minus I omega t plus B exponential minus I theta 1 exponential minus I omega t. And you can write that down for all the microphones. To do these calculations, to do what I'm showing here, you need to reconstruct, to use the Hilbert transform to get fully complex signals. You have real signals from your microphones, you fabricate you take the Hilbert transform, you get the complex signals, and then you can write down exactly what is shown here. And you can get A and B by using, because you have 5 microphones, but you only need to get 2 constants A and B. So you use a mean square technique because you optimize. You have more data than you need for A and B. And if you have 10 microphones, it's even better. You get a better. So this is how you get it. You obtain. You see, you obtain A and B by actually doing that. And P is the vector of pressures that you get. You do that at various points in time, and you get the A and B. And actually, the reconstruction are the solid lines, while the points are the experimental data. So you see, the reconstruction is pretty good. You have to verify that what you are doing. Once you have A and B, you reconstruct the signals and see that it works. So from that, we can get the spin ratio, and then we can also analyze what goes on for a given situation, because what we see is that sometimes the system is standing, sometimes it's spinning, it moves around. It's not just purely standing. We've been able later on to get purely standing, purely spinning, but at the beginning we got something which was continuously shifting from standing to spinning. So if it's standing, you have red around here, blue around there, then this is neutral, and then you have blue here, red here. So this is positive heat release, negative heat release rate, and then we have essentially neutral. And this is how it looks in if you do an analysis of the motion, and you see that when it becomes red here, it becomes blue here, and vice versa. So it was already very interesting to see that the flames are responding to these azimuthal modes, that you have this behavior. When it's spinning, you really get, you see this red is here, and now it's here, and now it's there, and now it's there. And you have a truly spinning operation. These instabilities were not very powerful, 200 pascals. Well, that's already something, but it's still, we've been able now to get instabilities by above 1,000 pascals, 5,000, yes.
Can you hear it when it's spinning?
Oh, yes. No, what you hear is a frequency. The spinning is just seen by the microphones, because the microphones detect a signal which look like this. You see the waveforms that you get if you put all the signals on a scope or on your computer. You see something which looks like a wave, while if you have a standing mode, you see something which is standing here. You see there is a big difference between the two. And you go from one to the other. So it doesn't, the system doesn't stay, at least in these early experiments, the system was not staying on a given coupling mode. It was moving from one, spinning to standing, but you hear nothing because the frequency is the same. It's basically the same.
But you don't hear a difference.
No, you don't hear a difference. The frequency stays at about 800 hertz. Yeah. Yeah, there is no, the only way that you detect spinning from standing is using the microphone, multiple microphone. A single microphone will just give you a frequency. You cannot. But if you have many microphones, you can see that this is standing. Definitely when you look at that, standing. When you go here, this is spinning because you have this wave. The waves are moving by. You know. The motion is like that, and so it is manifested in the pressure. In fact, you can look at the spin ratio, and there is a distribution. When you look at the signal, you can actually see that most of it is standing, but you have some spinning motions, some in between. You see there is a distribution, slightly displaced with respect to 0. So the signals are like that. And when you analyze this, you can actually give a probability of having something in between, something. This is it. And in these experiments, we were using cups, flares, you know, this, yeah.
It's going at sonic velocity. Can you see the spin?
It goes at sonic velocity. The spinning goes, to see it, you look, for example, at the flames. This spins at the speed of sound. So you need a high-speed camera to follow that.
But in a normal situation, you can't hear it, can't see it.
You hear a frequency. You cannot see the, with your eyes, you cannot. With the camera, you do. I've shown it before. You will see it.
And I understood that.
Yes.
I want to know what I see when I'm looking at it in real time.
When you look at real time, we will see that. Actually, I have some films now. These are very nice. Yeah. Good. This is a calculation. This is a group in Serfax. The leader of that group is Thierry Poinceau. And they have LES calculations of this situation. So what you see here is a combustor. So what they did is a slice through the combustor. And let's do it again. And what you see is the pressure field as it spins around. So perhaps this is more visible. Again, this goes at very high speed. So but with your eye, you cannot. But here at the lower imaging, then you can see it. And what you see is that actually the injectors respond to the pressure. As the pressure comes in front of the injector either gives a little more or a little less reactance. And there is the transfer function there, and there is a response. So this is seen here. They developed this cylinder, and you can see up there it's the pressure, and down here are the flames dancing to this pressure field. You see, and you see that the injectors at certain points deliver a little more reactance. This was published. One of the papers was published in the proceedings of the French Academy of Science. We have this volume, and this is a full volume about research in combustion in France, oriented towards aeronautical applications. So there are many papers in this. Yeah, so that's very nice. It's you see here already calculations which represent completely the combustor and the oscillations. Yes.
Just to increase the interaction between the
Yes, yeah. The idea, what we notice is that at first, we tried many ways to trigger the instabilities. And at first, we didn't get them. So then we put the walls, half walls. And there was something. And then I thought maybe we should have more interactions between the various flames. So we designed cups of various angles, and we varied the angle. And for some, the instabilities are stronger. But now we have situations where you don't need a cup. But there, we had a cup, and it produced a good level of instability. This is the experiment of Jim Dawson and Nick Worth. They were looking from above. So that's interesting because you see the viewing is not very good on the side here. And their initial experiment was not as nice as ours. we had a full window, a quartz window. Each one of them is expensive, but and we break them from time to time because when the instability is powerful, it breaks, and so. But
not due to thermal shock.
Due to the thermal as well as mechanical vibrations, and finally, suddenly it breaks. Yeah. So this is their equipment. They have also a very large plenum here, and they have also this. You see, they do have a rod, a bluff body here. So the swell number is not very large here. And much of the stabilization is due to recirculation behind that. We don't have that. We have swirlers, just swirlers with no bluff body. But nevertheless, the data is very nice because you can see spinning from above. You see right here, the film is even nicer. You can see that the flames are interacting and it's moving like that all around. So these are spinning modes in this situation. What they did is to put a mirror here and look at the high-speed camera from here. And you see the walls this one is shorter than this one. So they are able also to change the spacing between the injectors. This is a design parameter. How many injectors will you put to get a homogeneous temperature at the end of the combustor? If you put too many, they will be very close to each other. It's very difficult. If you put too few, maybe the temperature will not be very good. So there is it's interesting to change the spacing, and they were able to change the spacing. We get back here to our combustor, and what we see here is from the side the behavior of the flame. And again, red is positive intensity, blue is negative. And what we see here at the bottom is the pressure. And the idea is to see what happens between the heat release and the pressure. So this viewing window corresponds to just that, while the pressure is calculated all over. You see, we calculate the whole pressure field, but like that, we look at only these three flames here, and you can see immediately that the pressure and the heat release fluctuation is in phase. Let's do it again. You see, so this case, you do have this Rayleigh criterion is satisfied. The pressure and the heat release are in phase. All right, so we've done that analysis. We see that the pressure is in phase with the heat release rate fluctuations in a standing mode in this case, and the pressure fluctuations, you see, they are in phase. The idea was now to use these matrix injectors instead of using the, the swirling injectors. It's interesting to use these matrices because they produce laminar flames. So you simplify the problem. Instead of having a turbulent flame, instead of having the dynamics of these swirling turbulent flames, you have just conical flames. And of course, we know very well these conical flames. We have studied that previously. You've seen some of these results. So we make the problem simpler, and we have these matrix injectors. And this is the device. It accommodates these injectors. This is how the flames look like on these matrices. There is the waveguide outlet, again, between these injectors. We have these quartz windows on the outer and inner side of this device. This shows the dimensions, the hole sizes. It shows also that we have here microphones which are located on the plenum, as well as microphones located on the chamber, the high-speed camera, another camera here. So you can see the dimensions is typically an outer diameter of 0.4 meters, 40 centimeters. That's reasonable. It's a good size. If you diminish the size, you increase the frequency. So are the flames susceptible in the higher frequency range? That may be less easy. For example, Dawson and Worth are using ethylene because ethylene is more with propane. They are not able to get instability. So it shows that it's harder if you have a small diameter. So this is the spinning mode that goes like that, and that's the standing mode that is seen in this device. Now you see the injectors are these matrix injectors. And there are various areas. For example, here you get the standing mode. Here you have an axial mode. And here we have something unusual. It's a slanted mode. You will see how it looks. And these are spinning. So it gives you an idea of what happens.
What is the parameter phi?
It's the equivalence ratio. So you change the equivalence ratio. So here you are in the rich side, slightly rich, while here you are on the lean side. And UB is the bulk velocity of injection. So let's look at the film. So now this is done with a simple camera. It's not a high-speed camera. So let's look at what goes on as we, in this case. So this is the combustor. In this case, we ignite it with a spark, but then we take out this wire. It's extracted from the chamber. Like that, everything is perfectly smooth. There is not something that may keep a standing mode somewhere. So it's really clean. Injectors. So we will see spinning, standing, and slanted modes in principle. Yeah, it's moving. Is it moving? It's not moving. No. It had stopped to move. Now it's moving. So first of all, this is a spinning mode. Oops, sorry. What did I do? Let's go here. Yeah, no. Spinning mode. And you see the spinning. You can see here. So this rotates at high speed, at the speed of sound, essentially. Now this is the standing mode. It's a different place in the... And you see now it goes on one side and the other, almost, yes. And this is the slanted mode. So it's a combination between longitudinal oscillation and the standing mode. In fact, it looks, the standing mode, this slanted mode, looks like when you are in a stadium and people stand up and then go down. There is a wave going on. It looks a little bit like that. It's look like the, how do you call that? The what? There is a word in when people do that and it. What is it? It's a Mexican wave? Okay, all right, maybe. So anyway, that's how it looks. So, in fact, what we found in this combustor with these injectors is that you could have a standing mode, you could have the spinning mode, they would be steady. And in this case, much was driven by the plenum, what was happening in the plenum. In the other case, it was more the chamber, but in this case, it's the plenum. And so the nodal line can be actually changes, can be placed like that, or can be placed like this. And you see that the flames which are close to the nodal line are rather different from the flames which are perpendicular to this nodal line. You see the where you are at the very high pressure, many of the flames around are apparently blown off, you know, while when you are close to the nodal line, all the flames are there. There is a difference. Even by the eye, you can see that difference. Now, let's see how it goes. So again, what you see here is this standing mode and the nodal line. And let's examine now the situation for a given injector. So this is an injector close to the nodal line. You see the injector is not far from the nodal line. And we can see that in what happens here. Yeah. So the flames execute a motion, but not very large, because here the pressure is essentially close to zero. There is not much of a perturbation in pressure. There are perturbations in velocity, but not so much as immutable velocities, but not so much in terms of pressure. So there is not much going on here. The heat release fluctuation is rather low. There is a little bit of heat release fluctuation here. Let's go now to the other case where you are perpendicular to the nodal line. And here you see that the flames are very strongly changing very strongly when you are in a region where the pressure moves, where the pressure fluctuation is large. And of course, it looks a little bit like what we've seen before for these matrix burners. You see there is a pulse of heat release taking place at a moment in the cycle. It's quite visible here. Let's do it again. Yeah, here, that's the pulse. So at one point in the cycle, there is a strong pulse. So the flames in this configuration act in a different way. If they are at the maximum pressure position or near the maximum, there is a very strong fluctuation in the heat release. When they are close to the nodal line, not much is happening. And this is in between. So there is still motion. You see, as you move away from the nodal line, there is definitely heat release fluctuations taking place. When we look at the pressure signals and the photomultiplier, so we cannot place the pressure exactly at the same point as the photomultiplier, but you can reconstruct the pressure field and you can measure the photomultiplier intensity, and you see that they are essentially in phase here. So there is a phase match between the microphone and the heat release, for example, right here. If we look at this level here, it is also true. So P4, PM1. Yeah, these are in fact two signals for P4 and PM1 right here. And this is, there is a, I think, yeah, and for these two, again, we are looking essentially at this point here. If we look at the signal at the first harmonic, they are also in phase. So this is in phase. This is at the basic frequency around 400 hertz, 500 hertz. And this is also true for the first harmonic. And in the chamber, the microphones look like that. This is a spinning mode this time. And you see that in the chamber as well as in the plenum, the signals have these wave shapes, almost like in a textbook, where you see a spinning mode. So this is true. Yeah, you see here, as I told you, the flames which are away from the nodal line look like that. The flames which are close to the nodal line are not so much affected. These are affected, and they have a very strong motion in the vertical direction. Okay, there is also an analysis of the slanted mode. This was very unusual as a mode. It turns out, yes?
In a combustion engine,
Yes.
you use a strobe light to
Yeah.
make the shaft appear to stand still. If you were to feed a swirl frequency into a strobe light,
Yes.
would you be able to see the individual flames in swirling flame?
Using stroboscopy.
Yeah.
Stroboscopy with Schlieren. If you make Schlieren and use stroboscopy, you can actually see the motion. Yes.
Okay.
Yeah. Yeah. But it's better to use high-speed cameras, and now we have this very nice hardware. It's more difficult, to do, for example, Schlieren with a curved wall and so on. It's difficult. So for simple flames, we've done it. And for example, the films that I've shown, you remember, for conical flames, initially were obtained stroboscopically by doing Schlieren and using frequencies which were like 100 hertz. So you have 50 hertz and for the stroboscopy, and a little bit above 50 hertz, so on. Yeah. This shows more or less this slanted mode, and I'm not going to describe that in all details. But what is interesting also that no, it's still the spinning mode. So what we found, which is unusual, is that the nodal line under spinning configurations is not exactly at the same angle in the chamber and in the plenum. You would expect this to have the same nodal lines in the chamber and the plenum, but that's not quite true. You see that the phase are slightly different from the chamber and from the plenum. And this is explained in a paper. There is we explained that in one of these papers that we published. The explanation is that the flame itself introduces a phase, and as a consequence, the nodal lines are not exactly the same in the plenum and in the chamber. All right, so now this is a slanted mode. Again, we are not going to look at all the details here, but what is interesting here is that in this case, this shows the light intensity. So it has the features of a spinning mode, but it looks like a wave somewhat, but it looks different from a purely spinning wave. And the explanation for this slanted mode is that at the frequency of operation, when you change the velocity fluctuation, when you increase the velocity fluctuation, the phase difference between the velocity and the heat release also changes. So that's an effect directly of the describing function. And what you see here is that this is between u prime and q prime, and this is between u prime and q prime. Yeah. So there is a change in the phase, and also it has an effect on the gain. So by changing as the velocity is increasing, the phase is changing and the gain is changing. And this, if you assume that all these injectors get the same fluctuation of velocity, because of what I've just shown, what you get is a difference in the levels that you find at the various locations here. And you get this wave-like configuration. You start, one assumes that at the injectors, the velocity signals are in phase, but because of this behavior here, as you increase the level of oscillation of the velocity, what you get is something like that. You get you put a phase in which is different for the different levels of velocity, and you get something like that. So basically, you reconstruct something which is very close to what you measure here. You see, this is reconstructed by assuming this. You reconstruct that using the describing function, and you get something which looks like that. So the slanted mode can be explained because of these nonlinear effects. It's unusual. It's very unusual to have something like that. So, okay, so this summarizes some of the findings here. One can explain all sorts of things with this describing function. You see, this is specifically for this slanted mode. It's the nonlinear response of these elements produces this strange behavior. Then we went to the spray. In fact, all the data previously was just for air and propane, but in practical engines, you have a spray. So we decided to have now injectors injecting a spray. This device has about 100 kilowatts of power. So each spray, because it's 16 injectors, each spray is a small spray. It's not much material that is being injected, and so that's a difficult problem. To have a good, you need hollow cone pressure atomizers which produce a hollow cone, And there is only one company in France which is capable of producing these very tiny little injectors, but they produced it for us. It's not cheap, but that's it. In addition, we decided to put photomultipliers all over so that we could see what happens to each of these injectors. We have the microphones, so we have 8 microphones on the chamber, 8 photomultipliers, and 8 microphones in the plenum. So that makes about 24 signals. So now you really get big data. This is really big, and all of this is sampled at a high frequency, so you get a lot of data. And let me show you one nice result here. We start, it's stable, and it becomes unstable as the walls heat up. And it becomes so unstable that you can extinguish some flames. The frequency also changes, and suddenly some flames are extinguished. You briefly saw that. It's, you can, when the pressure fluctuation becomes sufficiently large, you get extinction. You get a few flames which are extinguished. The flames that are extinguished, let me first say that this is work done by Kevin Prieur, and he got the first Clean Sky Prize in Europe in 2018 from this work. So, you start from flames which are established here, and then suddenly you get this region where the flames are extinguished because the pressure fluctuation is very powerful. Yeah, it goes like that, sorry. It goes like here, and here you get extinction. You see, these are false colors, of course. The flames are blue, but it's easier to plot in red. And extinction is taking place when the level reaches about 4,000 pascals. So you need a very high level of pressure fluctuation. The flames that are extinguished are those that are submitted, that are close to the nodal line of pressure. But the nodal line of pressure is the maximum azimuthal velocity. So the flames are submitted to a very powerful sloshing motion in the transverse direction. They are displaced with respect to the injector, and if you shake them so strongly, extinction can take place. Of course, this depends on the quality of the stabilization itself. You know, if the flames are very well stabilized, they will be less receptive to this transverse motion. If they are not very well stabilized, they can be blown off by these oscillations. Yes? Sorry?
The cluster you have is essentially symmetrical.
Yes, everything is symmetrical.
What determines the direction of the nodal line?
The nodal line. Very often it's just, that's a big question, not yet fully answered. Why do we get standing modes? Why do we get spinning modes? We have some answers. One reason for getting standing modes is to have a slight asymmetry. For example, you put the spark plug and you leave it there. So there is a little bit, a small wire there, and it keeps the nodal line at that point. So one way to, the other thing that we noticed is that you may be spinning when you are at low amplitude, and as the amplitude is increasing, you get into the standing mode. In general, the standing mode appears as you increase the amplitude. But one of the reasons for having the standing mode is that it's a dissymmetry. So something is there. Everything is annular, but you have, let's say, for example, a hole in the quartz because you are putting there the spark plug, and that's yeah. That's a good question. So nevertheless, we still it's a problem. Why do we get this mode or that mode? Is for the same frequency? You see this combination of the two waves. You may have A and B, and if B is equal to 0, you have essentially spinning in one direction. A is equal to 0, spinning in the other direction. When you have the two of equal amplitudes, it's a standing mode. And it's the same solution for, so what we say, it's a degenerated situation. So this shows it in color. You can see that the flames here are blown out right here. And then they come back. After a while, the amplitude decreases and things, it starts again. All right, this gives you a list of our publications. So there was a lot of things to say, and it's all in these papers. This is just a very brief summary. And now let's more and more, yeah. But each of them is a new piece of work. It's another thing that we worked on, which is interesting, just to let you know, is that there is always a precessing vortex core in swirling injectors. And what is the effect of this PVC? A lot of people have worried about that. And what is interesting is that as soon as you put an acoustic wave, so for example, this PVC here is at 750 hertz. You put the acoustic wave FA here, and suddenly you get a frequency coming out at the difference between the PVC and the acoustics. So it shows that, that the system is nonlinear, and you produce an acoustic frequency which is just the difference between these two. So it comes in. It's interesting to see that you get this very nonlinear effect. And if you look at the features, you're able to produce, you see, this is a single injector. You're able to produce phase average images of the light intensity deviation from the mean distribution in the burner, gathered from above, and you have a yin and yang behavior at this interaction frequency. So this is explained in that paper. It's very funny to get something like that. It's all right. So this finishes this chapter. And now let's go to see sorry for that. I should have, okay. Let's close it. All right, so this is done. That's done. And now the next topic is to look at very briefly on another phenomenon, which is hysteresis. What we have here is we are looking at situations where the modes that we get, so it comes back to this question, how do we get the standing mode, how do we get the spinning mode? So we are doing that again using these matrix injectors. We have this configuration here. And what we've done is to look at what happens in this whole region. So here we have the longitudinal mode. All over the place you have some sort of chugging mode. Here we have a spinning mode. So if you go at 1.4 and 1, you get a spinning mode. Here you get a standing mode, and in this region here, you get a dual mode. That is, it may be spinning or it may be standing. And this depends on the way you get there. If you are here and you get there from a spinning situation, you get a spinning mode. And if you're here standing and you go here, you get a standing mode. So basically, this is the spinning mode. This is a standing mode. And you see here, if you are going that way, you get what I was saying. You get to a situation where you are essentially spinning, and if you go the other way, you're essentially standing. So there is a hysteresis loop. In this way, you get spinning. In that way, you get standing. And this can be manifested. For example, you place a microphone here and another one here. And when you have chugging, you have all this moves around everywhere. So you can see that on your scope. It's like a Lissajous sort of configuration. And when you have spinning, you have something like that coming out. And this is the case where you have, again, chugging. But if you go the other way, you get standing, and you see that standing is right there. So in the standing case, you are like that. In the spinning case, you are like that. So the outcome of that depends on the way you are going to this region. Okay? All right, so that's another. So in fact, the history is important. Sometimes what you get as a mode can be spinning, or sometimes it can be standing, but it is based on the history. All right. The next is to tell you a little bit about computations, because we've seen already an example where computations, full computations, can be very useful. So give you a small historical perspective on computations, and then look at dynamical problems. So laminar flame dynamics, we've seen already a few examples. Large eddy simulation of turbulent flames, this is what we need. We've done some ignition. There is a whole chapter on ignition that I will also detail, and azimuthal instabilities in other systems. So I call that computational flame dynamics. So it looks like CFD, but it's a little different, because CFD started really in the 1950s with the computers. In the 1950s, this became something important. It was very difficult in those years. It started we got more resources, and it became a little more easier. And it has continuously improved. You know, at first we were just being able to do two-dimensional calculations, and later on we did multiple three-dimensional calculations. In combustion, it's even more difficult, because you have to handle the reaction. How do you handle reaction? So the new CFD, the fact that you calculate flames, for example, rolled up in a vortex, we were very proud to do such calculations numerically, or to have an ignition in a turbulent flow field. This is in 2 dimensions still, using DNS, direct numerical simulation. But that was in the 1980s, 90s, in the beginning. So rather late. There is a time lag for combustion, because combustion is more complex. Now we have 3 groups of simulations. If we look at applications, a lot of the applications are done with Reynolds average Navier-Stokes equations. You take, this is for turbulent combustion, for example. You take the Navier-Stokes equations and you use averaging. The problem here is that you need models, models for everything, for the Reynolds stresses, for the turbulent fluxes, and the most difficult one is for combustion. How do you average the combustion, the reaction rates? So that's a big problem, has been extensively studied during all these years. A lot of models have been developed. This is really tough. On the other hand, direct simulation. You think, well, let's take the equations as they are and just plug them in the computer, use a very high, well-discretized equations, a nice algorithm, and put everything there. Unfortunately, this can be done, but on very small size flames. It's very difficult to do DNS. I can show you why. We'll see that in a minute. And in the middle, we have large eddy simulation. Large eddy simulation is what is used, for example, to do the meteorological predictions. They use LES. Basically, this is a calculation which is based on, so they use calculations as well as data assimilation. They have a lot of data from many places. So they use the data and they use the calculation. They combine the two to make a prediction for the next few days. And the predictions are pretty good. You know, they are, it's always remarkable to see in the morning they tell you in the evening it's going to rain, and it rains. Yeah? So you see fluid mechanics has become more and more predictable. Now you think that you can predict also the climate change over 100 years. That's a little more tricky because the resolution is not there. The size of the discretization is too large to. So for the moment, what is being predicted should be taken with some care. So anyway, so LES is in between here. This more or less looks like what we were able to do. In the 1950s, for example, Theodore von Karman and Penner solved the problem of the ozone flame, a flame which is formed by the decomposition of ozone with two reactions. So it takes 15 pages of calculations, and they were able to give the burning velocity of this ozone flame. And they were saying in their paper, we think that this method could be generalized to hydrocarbons, but it would have taken a lot of analytical calculations, very, very boring calculations. Even such a flame was very difficult. But in the 1960s, 70s, we started calculating hydrogen air flames and then hydrocarbon flames, simple flames. In those years, we were very interested in flames rolled up in vortices, and we started calculating non-homogeneous flames like that. At the same time, in those years, we did a lot of Reynolds average simulations, which are pretty good. They were also for the simple flames, we started calculating response functions, extinction, ignition, and in the 1990s, direct simulation developed. So you see some of the early calculations in direct simulation at the end of the 1980s. This is done now with LES, studying flashback, and these are some calculations of gas turbine combustion using LES. And now these were done in 3 dimensions here, around those years with a real injector. And these are multiple jets now. And this is the ignition of a full combustor. So as we go on, we now have the complex geometry, the injection of a liquid phase and ignition in this circumstance. We were also interested in, this was done at Fairfax. There is also a lot of work in IC engine LES now. And we worked also very much on the combustion at very high pressure in transcritical situations, above the critical point. you know, the thermodynamic critical point, and this is
Fuel.
this is oxygen injected at very low temperature, high pressure, above the critical point of oxygen. And this is difficult because then you have real gas effects, you have another complexity, and we are able now to calculate such flames. This I've shown, this calculation of the group at Fairfax. We were also calculating multiple jets in transcritical configurations, ignition in annular combustors, and this is a rocket engine with 42 injectors, all the geometry of the upstream, and we calculate that as well. So you see there is, I've shown what we have done more or less, but there is of course a lot of parallel calculations done by many other groups. So there is a great progress in what can be actually calculated. This is showing, and then we'll stop. This shows the growth of large eddy simulation in fluid mechanics. You can do that by, you put the words large eddy simulation, fluid mechanics, and you get this from the Web of Science. So you see that the starting point was around 1988. Very little LES in fluid mechanics before that time. And it goes to about 800 papers per year, 900 papers per year on LES. In combustion, this took a little more time. We started in this field around 1983, 1984, and now you have a lot of LES being done. And LES is, of course, very useful for combustion dynamics. So this is now, of course, the main tool to work on combustion dynamics from the numerical side. All right, let's stop for a quarter of an hour, and please come back at 11:16.